Hey everyone, and welcome back to the SaaS developer community. I'm your host, Gwen. So, last time we talked about compute storage separation and predicate pushdown. And I think we all enjoyed discussing fundamentals of distributed systems, those really basic ideas that are applicable in many different systems. So, I thought we can do a bit more of that. And I want to focus especially on the parts of distributed systems that people don't talk about that much. So there are some parts that everyone talked about again and again and again for the last decade. You know what I'm talking about. Cup theorem, leader election, log replication, maybe even atomic broadcast. This is all well known. On the other hand, it's been several decades since I've last heard anyone talk about fencing. Fencing is a really useful pattern in many systems, and it is especially critical in share everything systems. So share everything is pretty rare these days, which is why we're not talking that much about fencing, but I think it is making a comeback. So we're going to talk about share everything systems and why and how they do fencing. So it's going to be a bit of a long episode, so let me get to it, and I hope it will be interesting and exciting. So fencing is a general name for a collection of techniques, and all of those techniques have a single goal. Make sure that if you have an unhealthy process or an unhealthy node in the cluster, it cannot access a shared resource and cause corruption, inconsistencies, etc. So one of the reasons we don't talk that much about fencing these days is that there is not that many shared resources anymore. Today, most systems are what we call share nothing, or maybe more accurately, they share a bit of metadata. So some examples. Let's say we start with our usual single node Postgres database with its disk. Well, this is obviously share nothing. There is literally nothing you could share. But what if you have a primary and failover? So there is a bit of a shared information, such as who is the primary and who is the failover. The primary and failover both need to know that, the client needs to know that. So now you have a bit of shared information. This is still considered a shared nothing system for the most part. What if you shard the database? So now you have a bunch of primary, secondary pairs, which means that you have a lot of primaries. But those primaries don't share anything either. Each one is its independent, it has its own data, its own state. They cannot really corrupt each other. There is some shared information. The application needs to know which one of the shards has which data, but it's, again, share very little. Now, what about Kafka? Similar thing, right? If we have a broker, each broker has its own disks, it has its own data. There is some shared information, who is the leader, who is the controller, we need to handle that. But again, this is fairly classic for a share nothing system. Now that we know what is share nothing, what is shared everything? Well, this is the opposite, right? When you actually have a lot of processes that have access to the same resources, the resources are typically storage, files on disk, kind of thing. So let's take one of those systems we discussed last week where compute and storage is separate. If after separating compute and storage, you still give each compute node its own separate storage, its own separate volume, a virtual disk like EBS, this is still a shared nothing system. In a shared everything system or shared storage system, you'll have multiple nodes accessing the same disk, the same data at the same time. So one example would be something like you're running multiple web servers and they're behind the load balancer. So they're kind of like a cluster and they're all getting data from the same S3 bucket, or they're all getting data from the same database. This is like your web servers are now essentially a shared everything cluster. Everyone is accessing the exact same blocks, same resources, same data at more or less the same time. And there has to be a way to manage concurrency between all those accesses, especially around writes. Let's take Oracle RAC. Oracle Real Application Clusters is probably one of the most famous examples of share everything cluster. And in these scenarios, you have a lot of database nodes, a lot of Oracle nodes, and they're literally mounting the same disks on all nodes of the cluster. So replication, there is no replication between the database nodes as you would have in Kafka nodes kind of scenario. Replication is handled, if at all, by the storage layer itself. So it gives you this nice separation of concerns. Apache Pulsar, my understanding is that it has a similar pattern. You have the compute nodes, storage nodes do replication, and all the compute nodes can access all the storage nodes. So there's a lot of benefits for share everything system. As you can imagine, you can very easily load balance your compute to talk to different nodes, add more compute, remove compute. You don't need to move data, copy data around. If you want a new compute node, you just spin it up and point it to the shared data source. Your compute nodes don't have to worry about replication. It saves CPU. You have nice separation of concern. And failover is typically very fast because your storage is always right there. So all kinds of really good things. And the reason why you don't see more of those more or less good things is that, at least partially, for a very long time, share everything on the block storage level was basically impossible in cloud native systems. Cloud providers wouldn't let you mount the same disks on two nodes. Kubernetes would let you do it, but it was extremely complex, only worked in certain scenarios, certain storage. And Kubernetes in general has this complex relationship with persistent storage. So I don't think it was common to really go there. So for about a decade or so, we mostly built shared nothing system, which is why I don't even have many cool examples of share everything systems to give you. But this is the place where we have some exciting news. AWS now started supporting attaching taking one EBS volume and attaching multiple machines to it. Not only do they do that, they're actually doing it for, I think, IO1 and IO2. Both of them are types of EBS that are very appropriate and highly recommended for database systems. It's SSDs, it has really good guarantees, latency and throughput, availability, all those things. So this is kind of exciting news after decades that you couldn't even think about connecting two databases to the same disk because it was literally impossible. It is now possible, and we can start architecting this type of systems again. And who knows, maybe we will see the rise of share everything systems. So I'm very excited about this idea. But it's not like, okay, now you just spin off two databases, connect them to the same disk, and everything is easy and fine. It has benefits, but you really need to architect the system for that. You cannot take a random database, point it to the shared disk, and expect good things. Because if it's not built to be a cluster, and if it's not really carefully architected, then a faulty node can still access this shared data storage. And if it does that, it can cause extreme damage. In shared nothing systems, a leader that went rogue and doesn't know that it's not supposed to be a leader anymore, it can cause damage. Like, it can write things it shouldn't, it can delete stuff that it should actually keep. Like, it's definitely, some stuff can happen, but it's not even comparable to just dumping stuff from memory to blocks on a shared disk without being connected to the rest of the cluster, which can be a lot more damaging. So it is imperative, in order to have a safe and consistent and working shared everything system, that you will have some way of blocking off a faulty node from writing to the disk. This is critical. So again, if your shared everything system is actually a bunch of web servers talking to the same database, this is not really a problem. Databases are meant to be shared. They have locks, they have concurrency controls. They make it very safe to share the same database with a lot of app servers. They were written for that. If you actually take several databases and point them to the same file on a file system, this is a very different story, and you have to think about it carefully, which is why we have fencing. This, as I mentioned in the beginning, this collection of mechanisms that you can use to guarantee that a bad node cannot corrupt good data. And there are two main fencing mechanisms. So the first one is what we call epochs or generations. And I'll take Kafka Stream again as an example. If you have Kafka Streams, you're probably running it in exactly once mode. And in that scenario, it's really important, you have those tasks. Tasks have a consumer and a producer, and they always consume from a partition and produce to a partition. And it's super important that you only have one producer writing transactional data to a partition. If you have two of them, you can start getting duplicates, you can start having a mess in your transactions. Really terrible. So during rebalances, it's especially important that we will prevent the old producer from writing transactional data. So this is why we have transactional IDs and we have epochs. And during the rebalance, you have new producer pick up the transactional IDs that already exists, but it gets a higher epoch number. And it starts writing things with this higher epoch number. If the old producer comes up from the dead, what we call a zombie, then it still has the old epoch number, and therefore the broker can fence it off. It can say, oh, you're an old one, I'm sending you back an error, I am not accepting your request. So this is really great. It's a nice example of fencing, and this method is fantastic with the assumption that you have a distributed log, because you need this highly ordered shared data and the ability that even after failovers, you'll still have a lot of consistency in these shared logs that all the clients can look at. Kafka obviously has it. This is why it's Kafka. It's a distributed log. And if you have this thing, you can track epochs consistently, and you also need good control over the storage protocol, so it can detect when we have a zombie, and it can fence it off, and it can look at the epochs and all that. So if you have the systems that you're really architecting from scratch and you're going to have a distributed log anyway, then this method is a fantastic one. But what if you don't have all that? Well, the second method is applicable in most cases, and it's very often actually used either to glue onto an existing system or sometimes to get something simple and fast. So this method is called STONITH, shoot the other node in the head. I'm probably pronouncing it wrong. I'll write STONITH somewhere. I'm going to say it a lot though, so I hope you can get used to it. But the idea is that it's an abbreviation for shoot the other node in the head. Although very often, as you'll see, it actually means that the node is committing suicide. It's shooting itself. But so why do we shoot nodes? What's up with that? Well, we just talked about how some nodes can become zombies and they're dead, but they don't know they're dead, so they can still keep writing data and mess up stuff for the live nodes. Well, clearly zombies are very dangerous. They come back from the dead, they corrupt your data. So we really prefer dead processes, or maybe even better, dead machines, to zombies. Dead machines cannot do anything while zombies can mess stuff up. And we really want the only failure mode in our system to be completely dead, because then we don't have to worry about all those edge conditions of things coming back from the dead. And this is obviously really useful, really important when the priority of the system is to provide consistency, which is true for most databases. In those consistent systems, being dead and unavailable is much better than alive and messing up my data. So combine that with the idea that share everything systems are actually usually very good at failover, as it kind of makes sense to decide that even a node that mildly sneezes is actually dead and you want to shoot it off. I'm slightly exaggerating, but if you suspect fault, you default to killing it because you believe that this is the safer approach. That's kind of the basic assumption of any system that uses STONITH or shooting. So it's normally a solid plan. You reduce all failure modes to a single scenario, a dead node, and then you build a good system that is very resilient to dead nodes. Obviously, nothing is ever that simple. And when I mentioned on Twitter the other day that Hey, STONITH is actually a pretty cool thing. I'm wondering why we're not doing a bit more of it these days. A lot of people showed up and reminded me that it's actually a lot harder than it looks, and they reminded me of all the problems. So let's go over why we don't do STONITH all the time these days. Well, first of all, keep in mind that STONITH is not a replacement to leader election. It is a fencing mechanism. So you still need to elect a leader in a distributed system, which may have network partitions. After you elected the leader is the one that gets to shoot everyone else, or you may have some other protocols for how do you know who commits suicide. But without leader election mechanism and without a way to pass messages around about who is alive, who is dead, who is the leader, you really don't have a good chance of getting STONITH correct. You'll get a bunch of leaders shooting each other, and it will not end well. So remember that no matter what, you need a way to decide who gets to live and who doesn't, and to consistently distribute this information in a distributed system that has network partitions. But still, you need to elect a leader. No choice around it. Now, the second problem. You decided who needs to live and who needs to die in this complex scenario. How do you shoot it? And how do you know it's actually dead? Both things are very important. And remember, the node may be hanging, so just because you asked it, are you alive, and it doesn't answer, definitely doesn't mean it's actually dead. It may be dead to you, but still talking to the storage server and the clients and messing up all the bytes. So definitely don't believe that. It may also be just temporarily not responding, but the moment you stop trying to kill it, it will come back and mess your data. So definitely a hard problem in its own. And there are 3 common solutions to this problem. The first one is to have some kind of a combined heartbeat gossip protocol. So each node will ping other nodes, and it will keep saying, hey, are you alive? And the response will be, yes, I'm alive. And I'm also saying that those 4, 5, 6, 3, 2 other nodes are also alive. I also suspect that 7 and 8 are dead. Cool. And then with each heartbeat cycle, you get all this information from all the nodes in the system. And the next thing to do is to start reconciling it and making a decision about the state of the system. Do I only see a minority of live nodes, which means that I'm on the minority side of a network partition? Do I see something that is completely inconsistent? Do I missing a node that I was told I absolutely have to be able to see? They're all those, so it's separate in each system, but using this information, a node decides if it's supposed to kill itself. So obviously, the risks are A, the conditions are wrong, and the node may decide to kill itself when it shouldn't. Or maybe the bigger risk is that suicide attempts can fail. Just as an example, it's a very old one, but I think circa 20, I don't know, 2007 or something, there was a bug in the Linux process, in the Linux kernel with a race condition, and if 2 processes did shut down at the wrong order or at the same time, it could actually hang, and then it will not shut down, and the nodes will keep running. So, suicide is not as easy as the song sometimes say. There's a lot of cases of failure. So it's definitely not it's hard to just rely on this solution. Let me put it that way. Enter the second solution, which is applying hardware to the problem. You get a second independent node with a lot of extra reliability, but maybe not a lot of throughput. It doesn't even need to be particularly low latency. So you kind of get this kind of control plane network just for heartbeats and just for nodes telling each other to die. You get a bunch of hardware devices. There are hardware devices for shutting down nodes, for cutting them off from storage, all kinds of things like that. If you have physical machines in a data center and you can buy specialized hardware, this is kind of considered a good solution. Or at least best in class circa 2012 or something. Nowadays, of course, most of us don't have physical machines in data center. Why, if you would have physical machines in a data center, you'd probably be something like Amazon or Google. Cloud vendors have physical machines. Most of us don't. But cloud vendors have APIs. And you could use those APIs to ask nodes to terminate. You can call EC2 terminate node and tell it to kill a node. And very often, if you talk to your service providers, they will tell you, oh yeah, those requests go over a separate control plane network and not the data plane. So it does give you this extra redundancy. Yes, we actually do use hardware devices, so we have those nice guarantees. But the key thing is to actually make sure you understand exactly what the cloud vendor guarantees. When is a node actually dead? What part of the protocol do you need to watch for? What do you do if you get a different response? Is there any time limit, grace period? All those things have to be taken into account. So assuming you really understand what you're getting from the cloud vendor and how to really, really kill a node, this looks like a good option for the modern age. So in the past, something that was called real STONITH was pretty much using the heartbeat protocol and using dedicated hardware to make sure that you have the information and nodes really, really die when you need them to die. If you didn't have the hardware, and a lot of companies didn't, and you relied just on heartbeats and suicide, it was considered very questionable, even though it was extremely common. Even large financial applications used by very serious banks very often relied on suicide and heartbeats style of STONITH. On the other hand, a lot of other systems that were also supposed to work on what was called kind of common hardware, like Kafka, they actually ended up doing the extra work and writing the Raft-like distributed log with quorums, epochs, fencing, all those things in a shared log system. So you can see how the desire to not use specialized hardware led to certain decisions around system design. But let's say that you are building a cloud-native system today. I think it's worth asking yourself whether talking to the cloud vendor and using its APIs after you really understand them is a good alternative. I think it's very attractive. It's simple, it seems pretty clean, and especially if, unlike Kafka, you don't already have a good distributed log to build on. So you kind of need to get a system with distributed log and then build your entire fencing around it versus just shoot nodes, which may be a simpler solution. I think it's simpler. So remember, until very recently, you couldn't really do share everything systems in the cloud. So we don't really have a lot of experience running share everything systems in the cloud, definitely not ones with STONITH method. So my idea that it will be really cool to use STONITH is more of a thought experiment at this point. I may turn it into an experiment, but it's not exactly something that I officially recommend as system design. If you try it, definitely let me know how it went. I'll be very excited to hear about it. So, to summarize, we talked about shared nothing systems, and those are the most common systems today. You're all very familiar with them, so we only talked a bit about them. Then we talked about shared everything system and why they're not that common today, but maybe making a comeback. And then we talked about the patterns around fencing using epochs with a consistent distributed log, or using STONITH, and when to use each. And then we really talked about both the benefits of STONITH and the dangers of STONITH. So I hope you enjoyed this bit of a deep dive. And I really want to thank everyone on Twitter who responded to my wild idea about STONITH. people who agree with me that, oh yeah, using STONITH actually simplifies this build system and it could be really cool to do it in the cloud. And also the people who told me and reminded me, hey, STONITH is actually really hard. Don't just go around using STONITH everywhere. There is a chance you will get it wrong. And all your nodes are going to shoot each other or fail to shoot each other. And we are not even sure which one of those is worse. So thank you to Moshe Sadka, to Asymptotically Matt, to Todd Lipcon, who was my colleague back at Cloudera and implemented fencing both ways, probably multiple times. Joydeep Sensorama, who also worked on a variant of Hadoop and probably has a lot of experience with the systems. Sorkil Stray, Jeff Bin, Chris Wilson, Charity Major, Neil Bussing, Joe Stein, Avishai Ishalom, Mrinal Wadhawa, who reminded me that when in doubt, you kill the node is practically the slogan of Erlang. Esteban, who used to work on HBase, Travis Johnson, Roger Brederer, Shai Elkin, who was on my team on Kafka and knows everything about how Kafka can fail, and Joe Mageramov. So thank you all. I love tossing out wild ideas on Twitter and getting literally the most knowledgeable and experienced people in the world show up and teach me or remind me of aspects of the problem that I temporarily forgot about. And thank you for everyone who took the time to listen to me. I hope you enjoyed it. Don't forget to join our Slack if you haven't yet. And I hope to see you back in February.